we are going to understand how these different stationary phases really retain the compound. And let us start from the highly non-polar stationary phase. Thank you so much, Yogeshwar. Let us start our discussion from the highly non-polar stationary phase. And that becomes the 100% dimethyl polysiloxane. What is the highly non-polar stationary phase? Dimethyl polysiloxane, or in the short form, DMP. Now, why this dimethyl polysiloxane is a non-polar? Now, how many of you have the question? What makes the dimethyl polysiloxane a non-polar stationary phase? Is there not a chance of any polarized bond? Why there is no chance of the polarized bond? Yeah, Mohit, fantastic. I was expecting that response. So please understand, how many of you think this SI bond is SI bond which is part of this now, SiO bond? It's a part of the dimethyl polysiloxane. Now, is it a polar bond or a non-polar bond? What do you think about this one? Silicon and oxygen. Now, if you know the polar electronegativity values, the silicon has a 1.9 and oxygen has a 3.44. So what is the difference in the electronegativity between these two atoms, silicon and oxygen? Is it more than 0.5 or less than 0.5? It is obviously a more than 0.5, right? It is obviously more than 0.5. And if it is more than 0.5, what do you think? What do you think? The silicon and oxygen is going to be polar bond, right? Let us now think about this linkage, SiO-Si linkage, right? SiO-Si linkage. So what do you think? Whether SiO-Si linkage is a polar? Question mark. I missed question mark. So is SiO-Si polar or non-polar? Type in the chat box. Think about the example of carbon dioxide. How many of you remember the example of carbon dioxide we discussed earlier? Like carbon dioxide, the SiO-Si bond linkage is also in the symmetric geometry, or you can say, and because of that, though this SiO bond is a polar bond, but SiO-Si, because of the symmetric, it remains the highly non-polar bond. And if there is no polarized bond, this dimethyl polysiloxane remains what? Non-polar or polar? Type in the chat box. Right, amazing. So we understand this SiO-Si is not going to be polarized. Now think about carbon and this one. Carbon and this one, or carbon and hydrogen bond. This one, carbon hydrogen. Fantastic. So carbon hydrogen, we just learned that it is going to be a non-polar bond. So non-polar bond. So if everything is non-polar, what about carbon silicon? What about carbon silicon? Can anyone let me know in the chat box? What about carbon silicon? There is carbon silicon also. Carbon silicon. What is the carbon's electronegativity values? Can anyone Google and let me know in the chat box? Please let me know what is the electronegativity value of the carbon. I have the mobile too, so I can also do it. Okay, 2.55. Now, what is the difference you got here now, silicon and carbon? 2.6, I would say, so roughly 0.7, right? Roughly 0.7 or 0.65. So this carbon silicon can be a polar bond, but when you look at the symmetry here now, don't forget symmetry. What about the chances of the carbon silicon is going to be polarized because there is symmetry over here, and because of this now, you can easily realize that this bond is not going to be a polarized bond. So overall now, the only possibility is this now. Hydrocarbon is again the non-polar bond. This is a non-polar bond. This is a non-polar bond. So overall, there is no polar bond, and hence, can we conclude that the dimethyl polysiloxane aims to be a non-polar compound? Yes or no? Right. So what is the force of attraction that is going to take place in the non-polar compounds? What is the we talked about five different retention mechanisms, right? Starting from London dispersion force to dipole-dipole, hydrogen bonding, pi-pi interaction, boiling point. So out of this one now, being a non-polar compound, which retention mechanisms works over here? What is that? Is it a London dispersion force, which is applicable for highly non-polar compound like this one? So please understand that the retention of this column, that is the 100% dimethyl polysiloxane, follows the London dispersion force. Follows the London dispersion force. Suppose if you have this three compound, hexane, then comes the methanol, and then comes the acetone. Then comes. So let me know in the chat box where you expect which compound is going to retain for the longer time. Is hexane? Is that a methanol? Is that a acetone? Yeah. Why methanol, Dilshad? Please think again. Now this is the column which works on the non-polar principles. And think about just the like attracts like. La. How many of you heard about LAL, like attracts like? Almost similar principles. The non-polar columns attracts non-polar compounds. Now, which is a non-polar compound among these three? Is hexane a more non-polar? Is methanol a more non-polar? Is acetone a more non-polar? So answer comes to hexane. So if the hexane is a more non-polar, hexane retains on the stationary phase for more amount of time and ended eluting the late. I hope you understand this point. Type in yes in the chat box. So hexane remains over here. Now, what is the next non-polar compound? Methanol and acetone. Between these two, one which is more non-polar. I mean, both are polar, but if you compare the polarity, which remains the less polar? Which remains the less polar? Acetone is highly polar, Prabhu, and that is the methanol. So methanol can end up eluting at the between, and finally, acetone is highly polar, so elute at the beginning. I hope you understand this elution pattern. Type in U for understand in the chat box. Harpesh, thank you so much. Fantastic. So let us talk about the next important stationary phase, which is the 5% phenyl, diphenyl, sorry, and 95% dimethyl polysiloxane. Now, what is the diphenyl component is going to bring? What interaction can be brought by phenyl? As you know that the phenyl has the pi-pi interaction, yes or no? So pi-pi interaction is possible because of addition of phenyl, plus it also brings the hydrogen bonding. It also brings the hydrogen bonding. So two additional interactions are brought in, that is a pi-pi, and second one is hydrogen bonding. And we have the third one, that is what is this one? This is called as the London dispersion force. So how many interactions are possible in case of a 5% diphenyl plus 95% DMP stationary phase? Please type in 1, 2, 3, total 3 interactions possible. And what is the commercial example of this stationary phase? Maybe SC54, OB23, DB5, BP5, HP5. They are none other than this 5% diphenyl plus 95% dimethyl polysiloxane. So we talked about this, right? Phenyl increases the degree of hydrogen bonding, then pi-pi interaction, and there is a London dispersion force also. Let us talk about the mid-polar stationary phase. And this is a very popular stationary phase. Not this one, but the next one. So 35% dimethyl polysiloxane and 65% dimethyl polysiloxane. So you will have increased pi-pi interaction because now from 5%, the diphenyl component has grown to 35%. You will have the increased hydrogen bonding interaction because from 5%, the diphenyl component has increased to 35%. And these are the examples: DB35, DB35, BP35, RTX35, and ZB35. Again, in the case of 50% diphenyl, you will have increased interaction of pi-pi interaction and the hydrogen bonding. But this dimethyl polysiloxane, that is the London dispersion force, is going to get decreased as compared to 35% part. And these are the examples: DB17, RTX17, and BPX50. Now, this is one of the very popular stationary phase used in the gas chromatography. How many of you use 6% CYANOPROPYLPHENYL and 94% dimethyl polysiloxane, which is popularly known as DB624 or maybe DP624? Have you used this one? Type yes or no in the chat box. I am sure. Those who have operated the gas chromatography, yeah, Radhakrishna has used RTX 624, is one and the same stationary phase, by the way. Now, what are the different retention mechanisms possible? What are the different retention? By looking at this structure of this stationary phase, what are the possible interactions? What are the possible? So this brings what? Originally, the first one is London dispersion force. So I will write London dispersion force. Now, because of this phenyl, what is possible? We discussed, right? Because of phenyl, what is possible? The first one is the pi-pi interaction is possible, right? And phenyl is what? Phenyl is called as a basic compound, the Lewis base. Yes or no? Phenyl is the Lewis base. So Lewis base can form the hydrogen bond with the acidic compound or the acidic Lewis acid. So hydrogen bonding is possible. Hydrogen bonding is possible. Now, what is the another possibility? Look at this cyano compound, or if I have to explain this C triple bond N now. So if you look at the electronegativity values between carbon nitrogen, it is more than 0.5. So there is going to be a dipole-dipole interaction possible. So how many interactions are possible in case of 6% cyanopropylphenyl and 94% dimethyl polysiloxane? This is the first one, second one, third one, fourth one. So totally, the 4 different retention mechanisms are in the place in case of this stationary phase. Is that amazing, guys? Type in A for amazing in the chat box now. It's like the most versatile, not versatile, I will say, but most used stationary phase in the gas chromatography. And these are the commercial examples, right? So we discussed about this point, and then there are another stationary phases like 50% cyanopropyl, and this is very important, the polyethylene glycol. So what is the polyethylene glycol stationary phase? This is SiOSi, SiOH. So what is going to be the working principle behind the polyethylene glycol? It forms the hydrogen bond. It forms what? The hydrogen bond. And hydrogen bonding is a very strong in case of the polar compound. So which compound is going to attract on the polyethylene glycol stationary phase? Whether polar or non-polar? Polar or non-polar? Which compound retain or attracts to the polyethylene glycol stationary phase? Is it a polar or non-polar? Fantastic. Thank you so much, Radhakrishnan. It's going to be polar compound. Type in polar in the chat box. Always remember like attracts like.